Hello and welcome to another Aston Originals podcast from Aston History. I am Brian Sudlow, lecturer in history at Aston University. Today we're talking about photonics and about the history of technology and about the future of technology. It seems there's hardly a soul on the planet who does not have an electronic device of one sort or another. We live online, we work online, we entertain ourselves online, we study online, we shop online. Our communities are often online, and even the oddly named social media, a place that is so often profoundly unsociable, is for many people as real as the pub or the club. Certain countries even vote online, and every gaffe of every politician is now immortalized in memes and video clips across the internet, so we do not forget them. All of which suggests two things. First, the digital age is not just a technical revolution, but a period of social, political, and cultural evolution. As I like to tease my scientist friends and my engineering ones, there's no such thing as the purely technical. Every technical and scientific reality is socio-technical because it's the work of humans. We make our machines, and our machines make us. I've no doubt we'll come back to that in the course of our conversations. The second thing now. We've been living through an amazing technical revolution, most of which is hardly understood by non-specialists, well, like me, for example. Who amongst us really knows what happens beyond the screens that we swipe or scroll? Do we know? And should we care? We often don't, and we probably ought to. Especially in a world where the digital revolution goes every day faster and deeper into the very structures of the world around us. Well, fortunately, I'm joined today on the podcast by two colleagues who know exactly what happens beyond the screen, and it's my pleasure now to introduce them. First of all, Professor Andrew Ellis, 50th Anniversary Professor of Optical Communications at Aston University, where he's also the Deputy Director of the Institute of Photonic Technologies. Hello, Andrew. Nice to see you, and thank you for coming along. And also, sat opposite to me, Professor Wladek Forysiak, who likewise belongs to the Aston Institute of Photonic Technologies, but who also currently holds the chair in Highly Integrated Coherent Optical Fibre Communications, awarded by the Royal Academy of Engineering. Wladek, welcome also.
Hello.
Also joining me, as so often, is Dr. Ilaria Scaglia, Senior Lecturer in Modern History and a cultural historian with a special interest in technology, who's been thinking also about the parallels between our current revolution and previous ones. Ilaria, welcome again. So, Andrew and Wladek, thank you so much for coming on. This is part of a conversation that's really begun between photonics and history, and it's one that we're very excited about and we think is really important. But perhaps we could just start a little bit with your backgrounds. Photonics. How did you get into photonics? Well, perhaps it might be a good idea just to define photonics for the people watching or listening, but also say how you got into photonics in the first place.
How did I get into photonics? I actually tried to get out of photonics. When I was at school, we had a couple of physics teachers. Neither of them were particularly good at teaching the optics. So when I finally went to university, I picked the one university I visited that did not show me a laser lab. I deliberately tried to avoid it.
Right.
And then through an accident in the milk round, I ended up working for BT. Helped make the internet using photonics.
Okay, so that's how you got it. So are we talking about the 80s, the 1990s?
I've been in the 80s.
Be in the 80s, right. And photonics, just to clarify, what is photonics exactly?
So photonics is very similar to electronics. It's using light rather than electrons to gather information about the world, transport information around the world, and we would like to be able to store information around the world, but that's very difficult with photonics.
Okay.
Electronics is much better at.
Okay. So this is essentially, it's a part of engineering, and it's, instead of engineering using electricity, it's using, well, it does use electricity, doesn't it? But it's using the light.
Yes.
Right. Okay. Andrew, thank you very much. So in fact, you tried to avoid photonics, is what you were saying, and it's found you out. Wladek, over to you. How did you come into this area of engineering?
So my path was starting off in science and physics. Physics is what I enjoyed at school. Mm-hmm. So I went to study physics both at degree level and then subsequently for a PhD. But unlike Andrew, I was quite attracted by lasers. Lasers were very prominent at that time in various films. You can perhaps remember from even Goldfinger, James Bond in the 1960s being almost sliced open by a fictional laser at that time. So I thought, this is physics that I like. And I thought, maybe if I don't make it as a physicist, there's something useful to learn here, and I might be able to get a real job in industry if I don't make it as a physicist. So that's the way I got into it. But what I found after about 3 years after my PhD was that I wasn't enjoying the science so much, and I was looking for an opportunity to do something more useful, something that I could describe in simple terms to my mother, for example. This is what I do, and this is what it's used for. So I took the opportunity at that time to take the skills that I'd learnt in and around lasers and transport them into the engineering field, where photonics at that time in the early 90s was quite a relatively new term. So in fact, I came here to Aston University as one of the first postdocs to join the then fledgling photonics research group. And in fact, we had a conversation about whether the group should be named the optoelectronics group, this connection to electronics that Andrew mentioned, or photonics. And we were plumbed for photonics as a slightly more modern term, and indeed as a term that was distinct from optoelectronics being used by another very prominent university in the UK.
Okay. So, it's good that you chose the term that then became very, very successful, isn't it? I think you've picked up on something that I think is very fascinating for science and technology, but also in a cultural sense, which is that often what drives us is how these things appeal to our imaginations, and quite. I'm thinking back to my own childhood. The lasers of Star Wars and things like this were deeply engraved on the imagination. Imagination is huge, isn't it? Within the history of technology, Ilaria, don't you find? I think we can think of Jules Verne and all sorts of figures along that. Almost the very first film that was made, Voyage dans la Lune of Georges Méliès, is the story of a trip to the moon.
Yes, and what always struck me was the fact that either imagination was positive, was charming, was dreamlike, or it was scary, it was catastrophic, it was the fear of that. And there seemed always to be very little in between, but it's striking historically. People have tended to go towards the extremes.
Yeah. We invent progress or we invent disaster. Yeah. Or maybe we invent them both, I don't know. Well, look, just let's take the positive line. Just for a second now, I said in my introduction that we are in the digital revolution. Anyone who's accessing this podcast is watching it on a digital device, necessarily, of who knows of what kind. I have 2 digital devices on the table. Andrew has his computer too. Essentially, we're living in the matrix, aren't we? To some degree, and yet at the same time, I think many of us are not really aware of what goes on beyond. So perhaps I can turn to the photonics engineers now and say, what does happen beyond our devices? We're all familiar with devices. Helen, I think we have a picture of devices somewhere, don't we? Doing what devices make us do, which is bump into other people and things like that. But what exactly happens beyond the screen, beyond the Google search that we launch and so on? What's going on technically?
So I noticed your diagram as all wireless devices. I like my devices actually plugged in with a wire. I get better performance. But what happens with those devices is the information that you're wanting to exchange somewhere else is converted to electromagnetic radiation. Around about 3 or 4 gigahertz bandwidth at the moment, with 5G and 6G coming on, that might increase to 10, 20 gigahertz or so. That then propagates to a base station in your home. That will be your Wi-Fi router. And if you're out and about, that'll be one of these big towers with base stations with equipment on the top. At that point, it's detected, analysed, and converted to pulses of light, which are transmitted over optical fibres. Those optical fibres are then routed to telephone exchanges, where again they're switched around. And these days, the majority of things that we do, that traffic is routed towards a data centre. And there you access the information that you want, or are routed on through your internet service provider to the peer that you're doing a video call with. And then the whole process is reversed. The signal is sent to another base station. That base station finds the device wirelessly and communicates the information, and the software on your phone or your laptop gives you the information in a format that you can understand.
So in fact, in a sense, this isn't a technology. This is a whole system. This is a world that's going on beyond the screen. There are networks, there are physical networks, but there are also necessarily social networks here. There are people who run data centers. There are engineers who are fixing hardware. Presumably, these things require software as well to make them run. So this is a complex technical network. Not in the sense of the network that's carrying the information, but a network of actors and factors, essentially making this all possible.
I think that sounds about right. You could even describe it as a network of networks.
A network of networks.
You know, we have local area networks, metropolitan area networks, wide area networks, all addressing different distance scales and at different points in the communication path that Andrew described. That they come into effect. In terms of, Andrew mentioned that the critical role of the wireless connection in because that is the preferred way to connect to your device, which necessarily has to be mobile. And the point I wanted to add to his is that behind that, this network of optical fibers that's connecting those base stations to the data centers to other data centers is actually carrying the majority of the traffic around the globe today. So the wireless connection is doing all the local access, whereas the fiber is doing everything beyond that first kilometer or so. Increasingly, that fiber endpoint is getting closer and closer to the end user.
Ah, right. So, thank you, Helen. Thank you. I was going to ask if we could see the map. Now, Andrew, you were telling me this is out of date, but I mean, perhaps you could say a little bit about this map. Also, perhaps about what that might have looked like even in the 19th century.
So the first thing that I'll say is that there's some lines on there that I worked on. So one of those red ones going from the UK to America would be TAP-12. That was the first optically amplified submarine system that went in the year before the internet exploded. Okay. So we like to think that we helped make the internet popular. There's also one going down to South Africa, which is my first experience of the realities of commercial world there. They were suing the supplier with a rather severe stance, and the supplier would have gone bankrupt if we hadn't have found a technical solution to the problems. So that one was interesting as well. And there's the world's longest physical feature on there, CME-3, I think it is, that goes from the UK through the Mediterranean, through the Gulf, all the way out to Japan. It's the world's biggest man-made structure. So some very fascinating things on there. But if you look at the map from the 19th century, it's very similar in terms of the routes. And there we go. It's on the right there. So it's the same places, and it's because those are the sort of centres of trade and commerce around the world, where there's interesting things to communicate. It's out of date. If you look on the left, there's an awful lot more lines these days. There's a huge amount of capacity. Each one of those lines would have dwarfed the entire capacity that's shown on the other map. Every time we put one in, it's factor of 2 or even an order of magnitude more capacity than the previous one. The one that I built, we built with a 25-year lifetime, and within 10 years, the capacities of all the other cables that we put in were such that you wouldn't even bother using it for redundancy if there was a problem. It was that small a capacity, the rate of growth of the capacity of the cables. So.
It's probably worthwhile just explaining a little bit as well, isn't it? That the map we're looking at on the right-hand side there is the map of the telegraphic system, isn't it? Ilaria, would you like to sort of give us the historical perspective here? With, I mean, in 100 years' time, people will be looking back on the work that Andrew did across the ocean and seeing that in a historical perspective. Let's go back into the 19th century, and Andrew, I'll come back to you as well on this. But tell us a little bit about that telegraphic system.
Yes. First of all, the one thing I would like to note is the map itself. Historians love maps. We use them for all sorts of different purposes to indicate all sorts of traffic, how people moved. We will use a similar map to talk about ships, for instance, crossing the ocean. But what is striking to me about these maps is the fact that they represent something very physical. There are extremely large holes, I understand, like large tunnels, with an awful lot of cables in them. It's a lot of stuff. And it's physical stuff. It's stuff that you can touch. It's heavy stuff. It's made of material, of chemical. And I think that's one of the most important things to keep in mind here. Because both in the case of the telegraph, and I feel today with the case of the digital, if all you are is a user of the telegraph or a user of a telephone, you don't see any of that. All you see is your little message that magically gets to somebody else. And you imagine it in the air. You imagine it somewhat flying and disappearing. It's a bit like the concept of the cloud. You imagine it's a fluffy thing up there, very ethereal. But neither for the telegraph nor in our digital world and in the world that we're describing, that's true. These are very physical, big things you can touch, very tangible, made of stuff. And the problem is to transfer something from A to B. And the something can be an electrical impulse, or I understand now it's something that goes through light. It's basically a hole with light going through it, right? But it's a hole. It's something you can touch. And so I think that's the first big point. It's tough to get our head around. But so lead central to the story.
There's this paradox then, isn't there? That our experience of communication technologies feels quite intangible to the frontline user, as you say. It's just we send the message and there we go. We keep too many photos on Google Photos, and all we get are angry emails telling us to buy more data, and we're not thinking about the physical reality on the other side of that intangibility. I think we'll come back to that in a little while, if we may. Andrew, I know you have an interest in that 19th century story too. I mean, it was quite an endeavor, wasn't it, to lay the telegraphs, as it was indeed to lay these cables later.
It was a substantial effort. It started in 1816, apparently, with a link going to Hammersmith that was actually used to capture a criminal who thought he could escape the London police by getting on a train, and they got a message through to the police station at the other end on this telegraph. They first tried to do this transatlantic stuff in 1858 from Valentia in Ireland across to Newfoundland. And that system worked at about 7 words per minute. A minute to get that sentence out, which wouldn't be acceptable today. But that system eventually failed. Water got into the cable, and it failed. And it was J.J. Thomson from the electron who came up with a solution, which was a mirror galvanometer in 1866, which increased the sensitivity so they could tolerate that loss. And then it exploded. And within a few decades, we'd got the map that you see on the right there. It really had exploded. And that was running with Morse code.
With Morse code, and then would be translated at the opposite end.
That's right.
By the operators.
The 7 words per minute was manual operators, and then they had electronic system stuff.
It's definitely worth dwelling here Ilaria and Wladek, I'd like to come back to you a little bit on this. It's worth dwelling here on how this transformed life. I teach about the first Anglo-Afghan war at the end of the 1830s and early 1840s. It took news. It took months for the news of the British defeat. Took months for that news to get back, and in fact, the story only emerged in a succession of newspaper stories over a couple of weeks. But then, within 20 years or so, it became possible to send news from Calcutta to London in I think about half an hour. It was about half an hour to cover a distance which previously had taken weeks and weeks and weeks. We know the military in the Crimean War, the generals were very unhappy about the fact that the speed of news now getting back to the home front meant that the politicians could interfere in military strategy much more consistently than they might otherwise have done. These are the beginnings of an acceleration, aren't they, in the world that we see, in various ways. Ilaria, let me come back to you for a historical view on that, and perhaps back to Wladek for a contemporary one.
Yes, so it's a fascinating topic, one of those I like to cover a lot with my students and really get into, because it forces us to think about things we usually don't. And one first change was very tangible. A lot of people started new jobs, making wires, building tunnels. It created a whole new sector of the economy that wasn't there. But that's the most literal. A lot of people started to expect that these kind of communications would get faster and faster. And so the more prompt the capacity, the more prompt the message, the more impatient people would get already in the 19th century. Now, telegraphs were expensive. To send a telegram was expensive. To send a cablegram was even more expensive. I had to go across the ocean and to use this infrastructure. So people knew there wasn't something you would do as casually. You wouldn't just chat back and forth with your good friend in New York by cablegram, even if you were quite wealthy, never quite developed this way. On the other hand, the practice of sending a telegram to inform people grew quite quickly. To communicate death, for instance, it became the preferred method. It was used by the army to communicate casualties, right? The scene, we see it in movies, right? The scene of the mother at home and the person coming, with a telegram and everybody taking the head off. This is bad or bad news. But also to communicate happy news. Could be a wedding, could be, a victory or something else that happened. The expectation of being informed grew. And all of a sudden, why didn't you send a telegram? Why wasn't this communicated? And here I think we really see the echo of our contemporary days. It seems that the faster we're able to communicate, the faster we await the reply to come. And if that text is not returned within the hour, surely something's up. That is something that is well documented with the rise of the telegraph or other means of communication in the 19th century as well. And all of a sudden people started looking at the time. How long since the last communication? It started to matter more. And the language changes as a result. Because telegrams went by the word, right? People started to developing a whole new code to try to cram in as much as possible into those words.
So people might grumble today about text speak, but in fact, telegraphic speak was a thing, 100 years, more than 100 years before.
Well, I'm used to reading telegrams from the 19th century and from the early 20th century, and I'm often reminded by my own frustration when I read text, because they were equally economical with
the terms. Now, I'm going to quickly skip over the next 100 years here. I mean, just to note, en passant, that these communications, the telegram and so on, clearly had a remarkable transformative effect on all kinds of things, on the military, as I was mentioning, but also on commercial practices, on the development of commerce, the links between New York and London, as we know, the gravitation of those centers of economic power in the direction of North America and so on. I've made my own digital story actually about the automation of the New York Stock Exchange itself, an extraordinary process. And then up to the present day, Wladek, as a photonics engineer, you are sat atop this extraordinary revolution, and it's been transformative in so many ways, hasn't it, today?
It has indeed. And just to connect to what Ilaria was saying about telegrams, I remember being a best man 30-odd years ago, and one of the functions of a best man traditionally at that point was to read out the telegrams. I wonder if anyone's been sent a telegram in the last year or two, if they've been at a wedding. I certainly haven't heard. So the transformation has been extremely rapid over the last 20 to 30-year period, and some of that is to do with just the explosion in data carrying capacity that photonics offers over the electronic systems that we used up until those first systems that Andrew was talking about being involved with the deployment of back in the mid-90s, TAT-12, TAT-13. 12 and 13 stood for, I think, the 12th and 13th cables, or cable-like systems to be deployed across the Atlantic. So that transition happened really, really quickly since. So I was, for example, another thing you might remember from 20 years ago, dial-up. Sitting, waiting for all of those equalizations to happen with your phone line. All of that goes away once you have fiber optics coming right the way into your home, and the amount of data that you can transfer gets bigger and bigger. And to your point about speed, most of the fiber that's been deployed to date, it's a fantastic infrastructure, is so-called solid core fiber. So it has glass in the middle, different types of glass, engineered in a very special way in order to transmit the light in a controlled manner. Very recently, there's been a development in a modification of that, allowing some air, if you like, a hollow core fiber. And the interest in business, and the key feature of this is it allows light to travel a little bit faster. Light travels faster in air than it does in glass. And there's been a massive explosion of interest in business, particularly in banking, about using such a fiber, because they can move information from one bank to another just that fraction of a second faster.
That's interesting. Sorry, could I just, Helen, could we see a picture of a fiber cable? I think we've got a couple of examples here.
Yes. So actually,
it's probably a dated example, is it? Or
it is a dated. I try to speak. So this is an example. I think the larger one right in the middle is an example of a lightly armored cable that's probably used for submarine systems, I imagine. I think Andrew's nodding. He's much more familiar with these. He was involved in that deployment. And so you can see that there's in that element, you can't actually see the fiber because it's obscure, but you can see it in the left-hand one, the sky blue sheathing, and then right at the ends, perhaps elements of fibers. It's an extremely thin strand of glass. So if you look at the actual part of the glass that confines the light and prop it is only about 10 microns across. It's roughly 10 microns across in diameter. And most of what you see is all the protection, the plastic protection around that, and then the greater plastic sheathings around that. And then beyond that, and there are the kind of metallic protection layers, which are of different grades according to where the fiber cable is deployed, whether it's at deep sea, closer to the shore, or in terrestrial networks. They use different classes of these types of cables.
Okay. Am I right in thinking, however, that as successful as this extraordinary technology has been, there are also problems? There are problems on the horizon. There are concerns that photonic engineers have.
Absolutely. Problem that we highlighted a few years ago was the very fact everybody is now talking with the internet means that there's a lot of capacity. So there's two sorts of speed. The speed that Wladek was just talking about how quickly you get a piece of information from A to B. But there's also the speed of how much information do you get from A to B. And that's a tremendously large amount of information. And each piece of information takes a certain amount of energy. And so we became concerned maybe 10 years ago now that amount of energy was getting substantial. We were thinking maybe just the network part was going to take about 2% of the energy consumption of a developed country. And we were wrong. It was about 1.9% according to official figures. So it was large. And today in countries like Ireland, where they've got plentiful cooling water, the data centers that we connect to with those networks are consuming 20% of the country's energy infrastructure. Dublin has banned new data centers because they have not got enough wires to conduct the electricity around and service the population. So this energy consumption is getting worse and worse, and the amount of information we're trying to cram into each individual fiber is making it tighter and tighter to do that. So we're having to use new colors of lights, we're having to use electrical signal processing and all the tricks in the book to try and keep up with that growth. What we're trying to avoid doing is, if we want to double the capacity, having two cables. And then the hole that we put one of those cables in, which ideally has those hollow core fibers in it, so two cascaded holes, gets bigger, more roadworks, more cost, and people's bills start going up. We want to avoid that, but we also need to address that data center problem.
I think we're back here at the paradox we mentioned earlier, that the digital world seems intangible, it seems flighty. It's the cloud, isn't it? But in point of fact, underneath it all is this physical reality of data, of heat, of work. We're back with Newton in a way, aren't we? And what that means. I think we should dig a little bit more into some of these problems. We'll come back to that, I think, in our next conversation.